हाय डियर स्टूडेंट्स, अगर आप इन वीडियो लेक्चर्स का मैक्सिमम यूटिलाइजेशन करना चाहते हो तो आई थिंक आपको ये इंप्रूव सेशन डेफिनेटली फॉलो करना चाहिए और रिलीजियसली फॉलो करना चाहिए। इंप्रूव सेशन क्या है, इसका लिंक डिस्क्रिप्शन बॉक्स में है, तो जाओ उसको चेक करो। इसके अलावा अगर आप व्हाट्सएप ग्रुप ज्वाइन करना चाहते हो, और मुझे लगता है आपको करना भी चाहिए, तो आप क्या करो, हमारे वेबसाइट पे जाकर के अपने कॉन्टैक्ट डिटेल्स दे दो या फिर इस व्हाट्सएप नंबर पे जाकर के अपने कॉन्टैक्ट डिटेल्स दे दो, सो दैट हम आपको उसमें ऐड कर सके। चलो अब पढ़ना शुरू करते हैं।
Hi, welcome back. In this video we'll be learning about center of mass and momentum. So this is just a quick refresher on this chapter, and in the next video we'll talk about the collision and stuff. So let's start. Center of mass. Center of mass, it's the average location of the mass distribution. Okay, so hypothetically speaking, it is the point where the whole mass of the system is supposed to be concentrated. And mathematically the position of center of mass is a weighted sum of the individual masses. Okay, so summation of mi ri divided by summation of nmi. Now suppose I'm talking about x com, so this becomes summation of mi xi divided by summation of mi. Similarly goes for y com, similarly goes for z com. Okay, and this I goes from like 1 to n, like n number of particles are there, so we are going to take n additions. Okay, so next topic is center of gravity. So first of all, center of mass is based on mass. This center of gravity is based on weight, so it is the point about which the torque net on the system vanishes to 0, and this torque net is coming from the gravitational. In general case is coming from the gravitation. Okay, so based on the weight, it is the point about which the torque net of the gravitation on the system vanishes to 0, and the body can be perfectly balanced over this point. Now let's talk about the continuous distributions. So if we have like the mass is not discrete and it's distributed over, suppose a rod or maybe a disc or a triangle surface or something, so what do we have in this case? Like in discrete particle case, we have r com is summation of mi ri divided by summation ri, and this ri is vector, and so this summation of mi in the continuous sense, it's like basically summation of infinitely many differential elements, and that goes to integral dm, and this summation mi ri goes to integral rdm. So we have this formula in the continuous sense. R com is going to be integral rdm divided by integral of dm. Okay, so similarly we can get this x com value, y com value, and the z com value. So I'll do one simple calculation how to use this formula in the general case. Okay, so let's start with the simplest of all. This is a mass and having length L. Okay, so and this like mass is a uniform rod. Okay, so in this case, if I want to find the x com, obviously the y com is going to be 0, and even without doing any calculation, you must have that intuition. If the mass is uniform, the center of mass is going to lie at a distance of L by 2 from like either of the end. So let's calculate the center of mass location from this point. This is 0, 0. So x com will be x dm integral of dm. Okay, now this dm, that means I'm talking about a differential element at a distance of x. Okay, this is differential element dm, and this differential element dm is, suppose it's having a length of dl. Okay, or dx. So this dm is going to be mass per unit length into the length of the differential element, that is dx. So this integral becomes x dm is m by l dx, and this integration is integration of dm. Okay, and I can take m by l outside, and x dx is x square by 2, going from 0 to l is l square by 2. Okay, so l square by 2, and then integration of dm is nothing but m. So this is 1 by m cancel out, and this is going to give me l by 2. Okay, as we expected. Okay, so this is the simplest case, and simply if you have a circle, in case of a circle, you can calculate the center of mass is going to be at the center. Okay, so we are talking about this thing as a ring. Okay, and if this is a uniform disk, again the center of mass is going to be at the center. And then you have a bunch of formulas for like a triangular shape and a square shape, or a rectangular shape, or maybe a hemisphere, and like a solid sphere or spherical shell. So for the literature part, you can just see like in the notebook. In this videos and the upcoming videos, we are just going to like mainly focus on the problem solving aspect of it. Okay, so like whenever I'm going to use the formula for center of mass, I'll directly use the like result, okay, without deriving it. Okay, so I gave you a general overview like how I'm going to calculate the center of mass, and if you are able to figure out, the whole calculation for the center of mass is in continuous case is dependent on this dm. So if you are able to figure out this differential mass dm, it can be a linear element, it can be a surface element, it can be a volumetric element. So if you are able to figure out this dm, like half of the job is done, and it from their point like from that point on, it just becomes a normal like integration exercise. Okay, so let's move on to the next topic. Okay, so the next topic is linear momentum and its conservation. Okay, so we have this momentum formula is basically defined as mass into velocity, and like if we have n number of particles for a system, so suppose in the system we have n number of particles, and each particle is going to have like individual mass mi and individual velocity vi. So all of them can be in different direction. Okay, so all those vi can be in different direction. So if I'm going to calculate the net momentum of the system, I'm just going to add all mi and all vi as a vector. Okay, and that's going to give me my net momentum of the system. Okay, so we have from the Newton's law, and we have this f net on the system is rate of change of its total momentum. Okay, so for a system, the net force acting on it is basically rate of change of its total linear momentum, and if this f net goes to 0, that means there is no external force on the system, my dp by dt goes to 0. And if dp by dt goes to 0, that means my p system is constant. So what do we infer? So we infer if net force in the system is 0, the net linear momentum on the system's total linear momentum is constant. Okay, so if that is constant, that means for any time t or any state I or f, my system's momentum is going to be same. Okay, so for a system going from initial state to some final state, momentum of the system initial state is going to be equal to momentum of the system in the final state. Okay, so let's see some application for this theory. Okay, so here we have a simple scenario. There is a mass m kept on like a level ground, and it suddenly breaks into two masses m1 and m2. So how this breaking process happening, that's not a matter of concern. It can be some kind of internal explosion or something. So this mass, think of this mass as a grenade. Okay, and this grenade like blasts into two part, m1 and m2. So like in realistic scenario, this is going to be like many different particles, m1 m2 up to mn. Just for the sake of simplicity, I'm taking two masses, and the second mass is moving with a velocity of v2 or the speed of v2 towards right. Okay, and you're supposed to find the velocity of or the speed of m1. So we know there is no net force on the system, so this external force on the system is 0. And if these guys are if this guy is going to break into two part, that means during the breaking, this right hand side is going to exert some force, suppose f internal on the left hand side. Similarly, the left hand side is going to exert a force fi. If this is fi as a vector, this is going to be minus fi as a vector. So this I stands for the internal force, and this left hand side mass is going to exert a same force but in opposite direction on the right hand side guy. Okay, so again f net, if I'm going to add them up, f net goes to 0. Okay, so f net goes to 0, that means system's momentum must be conserved. Okay, so what is system's momentum initially? That is 0. The particle is at rest. Okay, so if system initial momentum is 0, system final momentum must be 0. So in this case, what is the final momentum of the system? If I'm going to calculate, suppose right hand side I'm taking I, upward I'm taking j. So p system final is m2 v2 I, and I don't know the velocity of this guy. I'm just going to call it v1, m2 v2 I plus m1 v1. Okay, and I know this has to be 0. Okay, so v1, as you should be able to see, is minus m2 v2 divided by m1. Okay, m1, and this is just in the I direction. Okay, so this v1 with a negative sign is in minus I. Okay, so if this guy goes to I, this guy must go to minus I, such that the total momentum goes to 0. I can extend the same problem in like in 3 particle case or 4 particle case. Suppose like this mass is there m or 3m, and it suddenly breaks down into like a multiple, like 3 particles, and the first particle stays there, call it m. The second particle like starts moving like at an angle of 30 degree. It's suppose m by 2, and with the velocity of v, what is the like momentum of the final particle. So again I'm going to write initial momentum 0, and I'll break this velocity into 2 parts, I and j, and again I'll just use p system is equal to 0, initial momentum 0, final momentum must be 0. So I'll get one equation, I'll solve for the unknown variable, and I'll get my answer. Okay, so this was a short introduction for the linear momentum and the conservation part, and the like basic idea of the center of mass and center of gravity. Okay, in the next video we'll be talking about the impulse, and then we'll learn more about the conservation of momentum and its application in general sense using problems. Okay, so stay tuned, we'll see you in the next video. Thank you. Hi, welcome back. In this video we'll discuss the motion of center of mass and some related concepts. Okay, and alongside we'll do some problems. Okay, so in the last video I gave you the formula. RCOM is mi ri, that summation over the summation of mi. Okay, so in this case this summation of mi is the total mass of the discrete particle system, and this is the mass weighted position vector summation. Okay, so and this is the same thing, RCM is equal to summation mi ri, I going from 1 to n, and divided by total mass of the system. So this is my m total. Okay, so if I'm going to differentiate it, I'll get dr by dt, and I can d by dt, and this whole thing is constant, so I can take it outside, and then differentiating this summation again for each term I'm going to take this mi outside the differentiation, and it's going to be dr by dt. So I hope it made sense, this statement. And again d by dt of RCM is basically velocity of the position of the velocity of the center of mass, and dri by dt is the individual velocity. So dri is the individual position vector of each particle, and the differentiation, time differentiation, is going to be the velocity of each particle. Okay, so this VCM, this becomes my VCM is summation of mi, and this is my vi, summation of mi vi divided by summation of mi. Okay, and this whole thing again I'm writing it as capital M, and I can write VCM is equal to 1 by m summation of mi vi. Okay, now this basically says the velocity of the center of mass is equal to the product of individual momentums divided by the total mass of the system. So you could also say VCM into m is equal to summation of mi vi. That basically says like the momentum of the center of mass. Okay, so this is the p of com. Okay, momentum of center of mass is equal to the sum of individual momentums. Okay, let's move on to the next topic, and that is basically the acceleration of the center of mass. So now we are going to differentiate that velocity relation. So we had this formula for velocity, it was VCM was 1 by m summation of mi vi. Okay, so if I'm going to differentiate both sides again with respect to time, I'll get d by dt of VCM, and then again d by dt of this whole thing. So just differentiate both sides, and 1 by m summation of mi vi, and this has to be taken as a derivative, and again I can take m outside, and this in this summation again mi outside for each each term, and this becomes summation of mi d by dt of vi again. And to the left we have d by dt of vcm, that is acm, and d by dt of vi is going to be ai. Okay, so putting back the values, I'll get my acm is 1 by m summation mi ai. So acceleration of the center of mass, so this is acceleration center of mass is basically 1 by m and summation of mi ai. Now think about it, if like I write mi ai as the like net force acting on the ith particle of the system. Okay, so mi ai is fi, I can also write acm is equal to 1 by m summation of fi. Okay, so this mi ai is the net force on the system. Okay, net force on the system, I can dissect that net force on the system as fi external plus some fi internal. Okay, so this fi is the net force on the ith particle, and I'm just going to break it down into two parts, fi external and fi internal. Now keep in mind, suppose I have two particles here, and this is particle A and particle B. If apart from the external forces that we have on this system, on the system of A and B, suppose this particle is attracting this particle with the force of F. Okay, so again this B is going to attract A with the same force F. Now the forces magnitudes are going to be same, but in the vector form, if I'm going to write this guy F, I'll write this guy minus F, or vice versa. So F net internal, so this I'm going to term it internal force. The summation of internal force is going to be F plus minus of F, and it's going to be 0 because they are always going to form the action reaction pair. Okay, so when I'm calculating the net force on the system, now say apart from this force I had some F1 here and F2 here. So if I'm going to talk about the net force on the system, I'm going to write F2 vector plus F1 vector, and this sum, this summation plus F and then plus of minus F is going to be some F net. Okay, and this term is always going to be 0. So F net on the system is always going to be comprised of the externally acting force, because these internally acting force are always going to sum towards 0. So if I'm going to write ACM is equal to 1 by m, and for this Fi, if I'm writing Fi external plus Fi internal, now this is the force on the ith particle. If I'm going to sum over like all the particles, this Fi, that is the force acting on the ith particle internal coming from the jth particle, is going to cancel when I'm going to talk about the force on the jth particle coming from the ith particle. Okay, so summation of this term internal always goes to 0. Okay, so F net, so I can write, so this basically says net force acting on the ith particle is Fi external plus Fi internal, and the internal force is produced due to the mutual interaction between the particles of the system, and from the Newton's third law, so basically same thing, Fij is equal to minus Fji, that basically the same thing that I explained over here. So summation of Fij, the total internal forces summation is going to be 0. So this ACM can be written as 1 by m summation of Fi external plus summation of Fi internal. And from this whatever discussion we did here regarding the internal force, this term is always going to be 0 for the whole system. Okay, so I'm just left with 1 by m summation of Fi external. Okay, so that is going to give me ACM. Okay, and again I can write m, if this is ACM is equal to 1 by m summation of Fi external, I can write m into ACM is equal to summation of Fi external, I goes from 1 to n, and again I can write m into ACM is equal to F net COM. The F net acting on the center of mass is basically summation of all the forces acting externally on each of the particles. Okay, so this concludes our motion of center mass for the velocity part and the acceleration part. Let's move on to the next topic.